I will start my presentation about our work on the multimodality models. And thank you, Jimmy, for the introduction. And I will introduce myself and the collaborator of this project. So my name is Tianle, and I'm the second year PhD student in the Boston University, advised by Dipti Gahadayarm. And this work is done with my advisor, Professor Dipti, along with some other folks in the BU and Google DeepMind. And in this work, we analyze and explore things around the multimodal large language models. Because now we have a lot of large foundational models, and because the input getting very complex, involving different modality like video, audio, text, etc. So we hope the model are able to process the information from different modality. But here the question comes is like whether the model are treating this information equally, or a model have any preference on specific modality. So that's a key aspect we are measuring in this project. And we will analyze from different angles. So we will first show what's the misalignment cases across different modality look like in our setting. And we will introduce our benchmark, which to test model around these cases. And then we do some probing, black box and white box analysis to fully understand why the model, what's the failure mode of this model, and why it happens foundationally in those large models. And finally, we will proposing a simple solution to help just a very quick fix for those cases. But that shows also some fundamental change in the models. Okay, so so our work is aligned on the multimodal, more specifically in the video audio models. So now we have a lot of video input along with the audios, but I think those input are pretty noisy. In most of time, what you see can slightly different from what you hear. Like you can always hear some background music, some background speech, which might have semantic difference between your video content and the visual content. So in this case, we hope the model first they are able to process the information separately and not be distracted by another misaligned modality. Like if you are asking what's happening in the what's the music in the background of this ad, you don't want the model to focus only on the visual content to answer and ignore the audio signal. And on the other side, it's the same. And second, we want the model to treat each modality equally. So if you're familiar with some visual language models, you might hear such cases that the model are having a larger preference for the language part, because that's very observative for the nowadays most of the multimodal, even multimodal large language model, the decoder part is still a language decoder. So something they are more likely to ignore the visual signal or but prefer on the language signal. But we hope to push these cases to a more general multimodal cases, like if we want to introduce more modality, like video, audio, and in the future maybe touch, or in medical cases like 3D modalities. We have those like lot of modality find individual encoders. Then in that case, will the model treat those kind of minor modality, like here is the video and audio equally, and that's what the behavior look like. That's the key we are analyzing. Yeah. So as I mentioned, our project is focusing on the misalignment issue to test out the modality preference, because in the misalignment cases, the model need to process the different modalities equally to fully understand the two semantic introduced from different modalities. And also, we noticed that in the current community, there's few work that really studying this aspect, because most of the video data set, they are assuming that all modalities agree. Like when you see the dog, you should expect like hearing a barking in the background. But in the real world, this case is very complex, and many times it could be different. Like in the you can have some visual, some video with no background sounds. You can having see a dog, but you actually hear a cat meowing from another side. So we studying this like conflict in the real world scenario. So that's the two aspects we are going to study. First is whether the model are robust under this misalignment, and second, if such misalignment happens, what model are prefer, or did they like treat this modality equally? And to study this, because there's very few like existing work that kind of like creates a good misalignment cases. So we put also like prepare our can create our benchmark. So we could how we define the align and misalignment cases is like this. So for align cases, we are targeting those which for both cases we are targeting the semantic alignment or misalignment. For the line cases, we can see what we see and what we hear having the same semantic. Like when both the like this case is both the audio and the visual are a dog. Visual is dog and the audio will be like a dog barking. And another misalignment cases we what we means more extreme is like we can create some cases we swap the background audio to some with the other semantic. Like here, what you can see a dog is barking in the visual, but what you hear is actually like some typewriter sounds. So the semantic are conflict in these scenarios. And then for both of these scenarios, we ask two questions. One is visual question, like what you see in this scenario, in this video. And also second question is we call audio questions. Please describe what you hear in the audio content so that we can test whether model are fully process these two like information resources individually and not distracted by each other. And because like text is also a very like common modality in the Ruby, so we also test like a text as like a destructor or like a misleading prompt or misleading information in the source. So here we what we do is quite simple. It's just we add like a misleading or distracting text at the front of each question, and then see whether when the text is misaligned with the video and audio, what will happen in this scenario. And to make our benchmark clean, we do a lot of filtering. First, we ensure that in our data set both the visual and audio part are corresponding to the semantic we labeled. And second, we do some human verification, ensure that there's no very specific other sounding source in the video could confuse the model. And second, we build this benchmark from the audio set, a very common and large scale video data sets, and we do a lot of like human ontology and also the quality filtering to ensure that all the semantic we mentioned in our data set is different enough to measure and it's on different like ontology lives. And then each video and audio is clean with the a single object sound or single semantic in the video or audio. And thus we have our benchmark on with like around 600 cases with like around 50 classes. And we do a lot of align and misaligned samples with like and also like text misaligned samples with about 5,000 samples to test. And then we probing the current model to see like the actually what's the failure mode of the models. We do two tests. The first is called black box analysis. We test out those models on our created benchmark. And second, we do some white box analysis for the open source model to see, I think essentially the attention map or attention distribution of this model and understand why they have such preference to a specific modality. And first, it's black for the black box probing area. We test for both open source and closed source models, and those are, I think, the SOTA models like theta farm model can process the video audio inputs. And like we said, the first question is like whether the model are robust under the visual and audio semantic misalignment. So here's our probing results. We for different models, open source and closed source model, we test for both the visual question and audio question as we saw. And the bar for each group, the bar on the left is the align and on the right is the misalignment cases. And we can see across all the models, you can find like a drop on the misalignment cases. Means that all the models are suffer from the destructor. But that's very I think very common. But what's more interesting, I think, is we found a different filter patterns across the different models. For those like Quinn and Video Llama, these two models, we can find like a very consistent drop across visual and audio questions. But for those Panda GPT and the Gemini family models, we found another failure mode. That's like the if you ask the visual question, the model almost doesn't drop with the distracted audio. But if you ask an audio question like what you hear, if the visual content is misaligned, is changed, model drops the accuracy to roughly like a random level. So we conclude that this actually showing two like preference behavior. Like for these two models, they are basically like treat these two modalities roughly more similar. But for Gemini and Panda GPT, they have a very strong visual bias. We call it like it is actually this model are seeing without listening. That's like whatever the content happens, whether it's aligned or misaligned, it trusts mainly the visual content. That also, I think, could probably we hypothesize this is because of the something in the training objectives that the model are having a strong visual bias, like they are trained to learn learn the shortcut that just only answer the question. Either even you prompt it for answer with audio only, you still look at the visual for the most as the very dominant information source. Okay. And then, secondly, we found that for the text side, that's very common. I think that all the models suffer from the misaligned text captions. And I think that's also kind of like close to what our initial hypothesis that like text is all very dominant and strong modality in those multimodal large language models. So text will be a very strong distractor if it happens misaligned with other modalities. Okay. And to understand why this happens, we also do some white box analysis to look at mainly the attention distribution to see what these things happens. So for the open source models, we first analysis this attention map across all the output token to all the input tokens. And then we separate the attention to three parts: the video tokens, audio token, and text tokens. And we average the attention value for both these token from different modalities and across all the layers and across all the tokens from specific modalities. And first, we found that definitely for most of the model, text is very dominant things that like text receive the most of the attentions. And videos and audios take very few attentions in most of scenarios we test. And then in those cases, we also found that videos like more frequently have like a slightly higher average attention than audio, but there's not necessarily be a very significant difference. And second, because we are testing around two questions when we ask model what's happening in the visual question, and also we ask the audio question, the model will have two different answers, right? So it will definitely have two distribution of their attentions. So in this case, we want to compare whether model are having different behavior if we really prompt it in different way, ask them to follow on different questions. So to compare the distribution difference, we use another matrix called coherence D matrix. It's basically compares the distribution difference from two distributions, and if the D is roughly like zero point 0.5 or less than zero point 0.2, it shows like a weak, very weak correlation between the like the two distribution like point two means that the two distribution are very close like this, and if larger than point 0.8 we means that these two distributions show a statistical difference. And then what we analysis is we compare the distribution when we ask model for a visual question and the attention for the when we ask model for an audio question. Because under these two cases, we actually want the model to focus on different information resources. Like when we ask visual, definitely we want the model to pay attention to the visual part. And for audio, we want the model to attend to the audio tokens. So we measure that whether model do this as we expected and how good they do this like attention shift. So first, this is for the visual token, we can see this coherence D value we measured. So first we can see for a slightly like a slight like maybe averaging point 0.2 um like uh coherence D value means a slight distribution shift when we ask differently. And also in the cases we found that this means that model actually do try a little bit on shifting their attention to the modality we prompted to. And then we found that in the misalignment cases, which is a red line, the model actually try to shift their attention more significantly. That means that on the that's also I think very like in our expectation that when the model or when the modality are misaligned, model definitely try to look at different things to retrieve different information and answer the question correctly. But we argue that because models still suffer from a consistent drop in most of models, so this distribution difference is not that significant enough to distinguish the information resources. And then yeah. And then secondly, we also found that I think there's like a side finding that we found the model try to look at the specific modality in the later layer. So for both the visual and audio model tokens, we can find the later layers layers are showing more sensitive to different modality tokens and do this like attention shift. And then, because we found the drop in the model, and we are thinking of whether we could have like a simple fix to improve the model. And we have a very simple idea called modality aware tuning. It's like, it's just we are creating a separate label for the model in the same video input, and just doing simple SFT supervised fine tuning for the models. That's, I think, inspired by the our previous finding that the model, most of the model might have such bias because the data we train is very like providing such shortcut. Like for the single video, we are only providing most of the time we're only providing one questions for the model to answer, and model don't need to specifically shift their attention across video and audio to answer the questions. And this might provide a shortcut that model learn the bias, learn the shortcuts in the misalignment cases. So to fix it, we provide a simple fix on the data set. That's like for the single video, we providing two specific, different, we ask two different questions. One about the like the visual question and another about the audio question. So that in my or my since then misalignment cases, it could have different labels, and model are forced to look at different modality to answer the questions. And by this training, we found the model actually this training works surprisingly well. That model can improve quite a lot after we trained it with such data. And the improvement is across both the video question and audio question and on both align and misalignment cases. Our query model is rising to something related comparable to the Gemini model's accuracy. And then beyond that, we're also showing that this training is It's generalizable to first the unseen classes, both alignment, misalignment cases. And this training is also benefit to the other benchmarks, even like from different domain, different data sources, and on like video, audio hallucination or other tasks. It shows like a generalized improvement. And then what's more interesting is like we found that this training can also benefit across modality. Remind that we are trained the model for only the visual question and visual question and audio questions, the misalignment across video and audios, but we didn't provide any training recipes about the text misalignments. But later on, in the previous black box findings, we found that the model also suffered from the misaligned text. But we found that if we train the model with the video and audio labels and the video audio misalignments, the model could generalize to the text misalignment with a very I think strong improvement. That means the model actually not only learn like answer audio video correctly, but just learn to look at the right modality, no matter what it what modality it is. And we further confirmed this by the previous white box analysis we did. So we compare the coherence D value for the model before it's a red line, and after training, which is a purple line. We found that the coherence D value is actually become much more higher after we train the model. So which means that the model actually learn to more actively shift their attention to the query token to the important query modality to the important modality we are query for the user want or they should retrieve information from. And by this, like more actively shifting the attention, the model can learn to a better information retrieval to the correct modality and more robust under the misalignment cases, and this showing the attention difference. So I think to summarize the our findings, like we found the current models are not robust under the semantic misalignment. And the model are most model are not treated those modality equally. And also like the bias happens especially like in Gemini, those closed source model. They are having a strongly like visual bias across among compared to the other modalities. And then why the model happens in this, it could be the data issue because the model learned a shortcut, or it could because the model have a very weak attention relocation. They are not good at paying attention to the queried or correct modality. And lastly, we found that simple alignment tuning on the data side could resolve this problem and improve the model's robustness and their attention behaviors. And that's all the all everything about this talk. And please let me know if any questions.